Okay, so this is part 2.4 of the chemistry series. So we're talking about atomic orbitals and quantum numbers. So just to recap, in the last video we talked about atomic orbitals, which are sort of the areas that the electron is probably going to be in. And so you have different shapes of orbitals. Some of the simplest, the 1s and 2s, are circular. The 2s has an extra circular node though. 2p, you've got these lobe shapes along the x, y and z axis. You've got three separate ones. 3s again, you've just got a circular like one, and then 3p gets a bit weirder because you've got all these different nodes, but again it's just sort of lobular along the x, y and z axis. And then 3d is again weirder because you've got four lobes now that follow two axes at once, and then you have this 3dz squared, which has two lobes but also like a donut shaped ring that is also part of the orbital in there. So some interesting shapes, but apart from knowing that these are sort of the areas in which the electrons reside, they're not that useful until we start looking at things called quantum numbers and until we start looking at orbital hybridization and bonding. So let's start looking at quantum numbers. So quantum numbers are numbers that describe where an electron is. So each electron has four separate quantum numbers. It has n, which is the principal quantum number. It has L, that is an L, you can write it as a nicer L if you would like. That's the angular quantum number or the orbital quantum number. There's M, which is the orbital quantum number is also L. There's M, which is the magnetic quantum number, and S, which is the spin quantum number. So what do these numbers mean? Well, going back to our first page, if we look at the 1s orbital, the 1 is our n. So n is equal to 1. Now, what do you think would be our L? So L is the orbital quantum number. So s orbitals are L equal to 0. P orbitals are L equal to 1. D orbitals are L equal to 2. So in this case L is equal to 0. In this case also M is equal to 0, and you'll see why in a second, and S is equal to plus or minus a half. So n equals 1, 2, 3 are sort of your energy levels. So that's what we were talking about before. You've got 1s, 2s, 3s, so that's your 1, 2, 3. L is like what types of orbitals can you have. So you can have s, p, d, you can have f. So 1s, you can only have 1 minus 1 is 0, so you can only have 0, which is the s orbital. But for example, in the n equals 3, 3 minus 1 is 2, 3 minus 2 is 1, and 3 minus 3 is 0. So you've got 2, 3, and 2, 1, and 0, which corresponds to your D, P, and S orbitals. So L is like orbital type. So D, P, S. M is your sort of orbital direction. So from minus L to L, these describe like the x, y, and z orbitals of the p. So p is L equals to 1. So minus 1, 0, 1 is your x, y, z p orbitals. And then the spin quantum number is just for each electron in each of those different configurations of each orbital. You can have two electrons, one spin up, one spin down, or one with spin 1/2 and one with spin minus 1/2. The reason behind it being a half is it's an eigenvalue for a quantum equation that you don't need to worry about. So, an example here, the 2p orbital. N is equal to 2, L is equal to 1 because it's the p orbital. So, remember, L can be values between n minus 1 and 0, so in this case it's 1. And M can be minus 1, 0, or 1, which is x, y, and z. So you've got 2 electrons in each, one spin up, one spin down, which you write as an arrow up or an arrow down. And that means that it's got a full, so this one has, this electron here has n equal to 2, L equal to 1, M equal to negative 1 is the x. They're not so readily assigned, but just for our case. And then S equal to half, which is the upspin. This one would be the same, but S equal to negative a half. So that's the downspin. So you have upspin and downspin electrons in each orbital configuration.